This is the luckiest maths teacher in the world. Thank you so much for tuning into this video on groups and rings, specifically involving matrices. So we're looking at set, which I'll call G, of matrices. So if the first four axioms hold, we call that set a group. So the first axiom, associativity, says that if you have an operation, usually addition or subtraction, you can put the brackets wherever. So it doesn't matter if I put them around the first two or the last two, I get the same result. So closure just means if you add or multiply, whichever one you're talking about, two elements in the set, you get another element of the set. Inverse means that if something is a member of the set, then its inverse is also in the set. And the last one, identity, just means the identity is in the set. So I called it E because sometimes we're talking about the additive identity, which would be the zero matrix, and sometimes we're talking about the multiplicative identity, which is I. You know, it has one along the leading diagonals and zeros everywhere else. So if those axioms hold, those four axioms hold, we say that the set is a group. So sometimes you might see one of them not written. For example, this last one just follows from the previous two. If the previous two are true, then the last one will be true. Because if two elements are closed under an operation in the set, and the inverses have to be in the set, then that means A operated with A inverse, which is the identity, will be in the set. So I'm just explaining that the fourth one follows from the previous two. Now note the operation, usually addition or multiplication, doesn't need to be commutative. Commutative means the order of the operation doesn't matter. We don't need this for a group. If we have a group where the operation's commutative, we call it an abelian group. But commutativity is not necessarily for it to be a group. A group only requires the first four axioms. A special type of group called an abelian group needs the first five. Now the three down the bottom are not needed at all for a group. They're extra ones for a ring. So a ring has to satisfy an abelian group for addition. So a ring is a set where the elements form an abelian group under addition, and then these three are also true, that multiplication is associative, the identity is in the set, and that the distributive law holds. When we're talking about matrices, we can take for granted associativity, multiplication, and addition is associative, and we can also take for granted the distributive law. So you don't need to prove them, you can just assume that they're true. Both multiplication and addition are associative for matrices, and multiplication is distributive over addition. So of course it is possible that you have a set of anything, in this case a set of matrices, that forms a group under multiplication but not addition, or vice versa. So we'll start off by looking at a very simple group under multiplication. So we're looking at the set G that contains this matrix and this matrix. So I is just the usual 2 by 2 identity matrix. So it turns out that this forms an abelian group under multiplication. So I could prove associativity by writing out, strings of A's and I's and showing that I get the same answer regardless of where I put the brackets, but I said before you can take it for granted. So closure is easy to show. I just have to show if I multiply two elements of the group, I get another one. So I know that if I multiply A and I together in whatever order, I just get A because I is the identity. Now if I multiply A by itself, I get I. A squared is equal to I. So it's impossible for me to take any of these matrices and multiply them together in such a way that I get something that's not in the group. I probably should have also mentioned that I squared is also I. So they are closed under multiplication. So inverses do exist in this group because A is its own inverse, I is its own inverse, and they are, of course, in the group. So if A is in the group, so too is its inverse. If I is in the group, so too is its inverse. So that means that this axiom holds. Now, the identity is clearly a member of the group as well. So that's why these two matrices together forms a group under multiplication. Now, it's also commutative because the order of multiplication doesn't matter in this set. It doesn't matter if you're just multiplying A by I or either one by itself. It doesn't matter the order in which you multiply them, you'll get the same answer. So note that that's generally not true for matrices. Generally, if you take two matrices, the order of multiplication does matter. So most groups of matrices under multiplication will not be abelian. It is, however, possible that you have cases like this. You have special subgroups of matrices where the order of multiplication doesn't matter. So this is an abelian group. This set G forms an abelian group under multiplication. Now, will it form a ring? The answer is no, because it doesn't even form a group under addition. It's a group under multiplication, but not under addition. Because even though these two matrices are associative under addition, the other axioms don't hold. For example, A plus I gives you a matrix that is not in the set. So that's why that doesn't hold. Inverses don't exist because now we're talking inverse for addition. The inverse of I, for example, so the I inverse under addition, I'm just going to call I inverse star, would actually be -1, 0, 0, -1. That's the matrix you need to add to I to get 0. That's not in the group. So that axiom doesn't hold. The identity is not in the group either. I is the multiplicative identity, but if we're talking about the operation of addition, the identity, the additive identity, is the 0 matrix, which is not in G. So this does not form a group under addition and therefore can't be a ring. All right, let's take a look at an example that is a little more interesting. Please pause and copy down anything you need. Let's look at G, the set of 3 by 3 lower triangular matrices. Remember, a matrix is lower triangular if this holds, Aij equals 0 whenever I is less than j. Just a fancy way of saying all the elements above the leading diagonal must be 0. Note any or all of these stars here can be 0. Let's determine whether or not this forms a group under addition and also for multiplication. So let's start by determining whether or not it forms a group under addition. So we know that addition is associative. I told you addition of matrices is always associative. Of course, because we're looking at 3 by 3 matrices, any member of the group can be added to any other member of the group. So we're all good there. So closure. So if I add together two lower triangular matrices, I get another lower triangular matrix. Of course, if I have zeros above the diagonal and I add it to another matrix with zeros above the diagonal, I just get zeros above the diagonal. So that's why it's closed. The set is closed under addition. So for inverses, yes, they will be a member of the group. The inverse of this matrix here, it will be the same. It will have zeros above the leading diagonal. All you have to do is take each of these elements and take the negative of it. So it'll be the negative of each of these stars, whatever they equal. Note, we're talking about inverses under addition here, not necessarily under multiplication. So then we'll look at the last one, identity. Well, it turns out that the additive identity for 3 by 3 matrices is a lower triangular matrix. It is, of course, this matrix here of all zeros. That's the additive identity. It is a lower triangular matrix because all its entries above the leading diagonal turn out to be zeros. As I said before, any or all of these stars can equal 0, so that means that the additive identity is indeed a member of this set. it is a lower triangular matrix. It turns out that addition is always commutative. It doesn't matter whether we're talking about lower triangular matrices or upper triangular matrices or whatever. Addition is always commutative between two matrices of the same size. You always get the same answer regardless of the order in which you add. So let's look at multiplication. Well, we know multiplication is always associative. Doesn't matter what type of matrix we're talking about. Now, it turns out if you multiply together any two lower triangular matrices, you get another lower triangular matrix. So that's all good. But the thing that fails here is inverses. There is no guarantee that a 3 by 3 lower triangular matrix is invertible. In fact, if any of its diagonal entries, this one, or this one, is equal to 0, it will not have an inverse at all. So its inverse definitely won't be in the group. Now, the identity will be in the group. The multiplicative identity is, of course, this matrix here, and it is lower triangular. It's also upper triangular, but it's lower triangular because all entries above the leading diagonal are 0. Now, in general, matrix multiplication is not commutative, so we can't say that it will be for this set here. So it turns out that this set G forms an abelian group under addition, but not under multiplication. However, multiplication is associative, and the identity, the multiplicative identity, is a member of this group. So the only other thing we need to check for determining whether or not it forms a ring is the distributive law. But I said that you could take that for granted because multiplication is always distributive over addition. And of course, it goes without saying, you can do any combination of multiplying and then adding these matrices together because they're all the same size 3 by 3. You'll never have a problem where you have two matrices that can't be added together or multiplied together. So the distributive law does actually hold here, and thus we conclude that G is a ring. So there are many other interesting subgroups and sub-rings of matrices that we'll learn about in the lesson. I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.